In this video, we're going to be going over what is an RC circuit and how to analyze an RC circuit and find certain variables when given a problem, like time constants, how long it takes to get the capacitor to a certain charge of its max charge, and things of that nature. Okay, so first off, what is an RC circuit? So an RC circuit is a circuit with a resistor and a capacitor hooked up to a battery or source of voltage. Okay, we know a capacitor connected to a battery, the charge equals its capacitance of the capacitor times the voltage of the battery. Now this Q equals CV is actually the max charge. Now it takes time for a capacitor to reach the maximum charge. Now an RC circuit is a very basic circuit, and we can look at it like this. I have a resistor and then a capacitor that is symbolized by those two equal lines. And we have this battery right here, and we're going to say that this battery, the EMF equals the voltage, because we are going to assume no internal resistance. This is going to be an ideal battery, so no internal resistance. And when you see a problem that talks about internal resistance, it is sometimes often labeled with an R. External resistance is labeled with a capital R. Okay. Now, at first, when the capacitor is charging, let's do a little axis right here. It charges fast, but as a certain point is reached, the charging slows down. So we'll have the charge right here and then time on our x-axis, and it charges really, really fast until it gets to a certain point, and then it levels off. So it has this sort of max charge, this asymptote, if you will, right here that it's never going to, cross. So I don't know if you've ever heard those commercials, I'm sure you have, for our advertisements. Not really commercials anymore, everybody's online and doing streaming services, but they'll tell you, well, it takes, like 10 minutes to reach, or like not even 10 minutes, like 5 minutes or 10 minutes, some like ridiculously short time to reach, 50 or 60% of the charge. You're like, man, that's really fast. And so you're like, I want that phone, or I want that electronic. Well, what they don't tell you is that the capacitor is charging exponentially. And so that means that it will charge really fast right here, but then we assume that that means that it's only going to take, if it takes, 3 minutes or 5 minutes to reach 50%, we think, oh man, that means my phone will be charged to 100% in, like 60, or excuse me, in like 6 minutes. And that's not the case. So now you're smarter than that, and you won't fall for those advertisements again. Okay, so this is how a capacitor charges, and we have an equation that allows us to find the charge of a capacitor after a certain time of connection. And this is that equation. And you'll see that we find that with an exponential, because the charge is increasing, and we will also see that it's decreasing exponentially. Okay, and you will see here that our time constant, we have this that's based on the resistor and the capacitance of the capacitor, hence the name RC circuit. So we have this equals the resistor in our circuit, and this is the capacitance of our capacitor in the circuit. And we call RC the Greek letter tau. And this is a lowercase tau. Now the units of the time constant are, if we have R, that would be ohms and farads, but another symbol for that is also seconds. And if we look at this right here, we have R. Well, we know that according to Ohm's law, voltage equals IR. So if we want to find R, we would say V divided by I. So this would be V divided by I. Then we have times C. Well, we know C is equal to Q, the charge, divided by the voltage. So we can say Q divided by V. And then if we look here, we have these volts. We know it's going to be volts. This right here, the V divided by I, is volts divided by amps times, and Q is in coulombs. And then V is still in volts. So then we see that these volts will cancel, and then we have coulombs divided by amps. And amps is just coulombs divided by seconds. We have coulombs right here. And then we know that when you're dividing, it's the same thing as multiplying by the reciprocal. So we could have coulombs times seconds divided by coulombs, in which case our coulombs cancel and we have seconds. So that's why RC can also be represented by seconds. Pretty cool. Okay, now that means that this Greek letter right here, tau, it also has a unit of seconds. And this is T equals RC. Just a fun fact is how long it takes to reach 63% of your Qmax. I don't know, just a fun fact by itself. Okay? Well, what if you want to find a particular charge at a particular time? Well, we can do that with this equation up here. Okay. Now, if you want to find the charge, we'll have Qmax here equals capacitance times voltage. Well, if you want to know an ideal batteries, because a lot of the problems you're given in these physics problems will assume an ideal battery, your Qmax is going to equal capacitance times your EMF. Because remember, voltage equals EMF minus current times internal resistance. Well, if you don't have any internal resistance, that means your R is going to equal 0. Therefore, that just goes away. So your V is just going to equal the EMF. So for an ideal battery, it would be capacitance times EMF. Now, what if you want to find the voltage on a capacitor? Well, let's draw our capacitor here. And say this is our equation. Q equals CV times T. You want to find it at a certain time. Well, if you did C, because we know Q, we just put up here, equals CV, right? So if we have CV times T equals, and this will be of an ideal battery. We'll do it of the ideal. It'll be E CE, 1 minus E minus T divided by tau, or RC. And this would be an equation for the voltage on a capacitor of an ideal battery. Now, if you see here, these C's will cancel and you just have voltage equals EMF times 1 minus E to the negative T divided by tau. All right, now, as the charge on our capacitor grows, as it gets bigger, we're going to see that our current gets smaller. So, say right here we have the Q, well, we'll say I max, we'll say I is up here. And as our capacitor charges in time, it's going to look like this. So you'll see, if we look it up here, as our capacitor charges, it's going up. And we'll see that the current is the exact inverse pattern of that. Okay. Now, if you want to find the current at a particular charging time or discharging time of your capacitor, this is the equation that you would use for that. You could also use tau. This is current at a specific time. So now that we have all of this information, what kind of questions can you expect to see on a test or homework? Well, let's do one. Okay, so we have a problem here that says a capacitor in an RC circuit has a capacitance of 30 microfarads, a resistance of 20 kiloohms, and a battery that has an EMF of 12 volts. That means we're considering no internal resistance. Calculate tau, the maximum charge, and the time for the capacitor to reach 99% of its max charge. All right, so we're going to solve this using the guess method. In physics, I have found that going slowly and methodically is the way to go. I have a tendency to just rush, and rushing is not our friend in physics. Okay, so this helps to kind of slow things down. So for the givens that we have, which is our G, we have that the circuit has a capacitance of 30 microfarads. So let's write that down. Capacitance equals 30 microfarads. Now micro is the same as 10 to the minus 6 farads. Then we see that we have a resistance of 20 kiloohms. Now kilo is 10 to the 3 ohms. And then we see that our battery has an EMF of 12 volts. Now the next part of the guess method is U, and that's our unknowns. So our unknowns are tau, Q max, and the time for the capacitor to reach 99% of its max charge. So we want to know tau, we want to know the maximum charge, and we want to know the time to reach 99% of Q max. All right, so what are some equations that we just learned? So we know that T, or tau, equals RC. We also know that Q max equals QC, or in an ideal battery, CE. And then we also know to find our charge at a particular time, our equation is QT equals Q max 1 minus E to the negative T divided by tau. Okay, The next part of our method is the S, which is to substitute in values that we have right here for these that we know. So we have that tau equals RC. Well, we know that R is 20 times 10 to the 3 farads times C, which we have as 30 times 10 to the minus 6 farads. And then we know that Q max equals, in this case, we don't know the charge. So if we did know the charge, we could put that in, but we don't know it. So we're just going to say capacitance times EMF. So we have Q max equals capacitance, which we know is 30 times 10 to the minus 6 farads, times EMF, which we know is 12 volts. So let's put these in our calculator. So for tau, we have 20 e to the 3 times 30 e to the minus 6. This is going to be 0.6, and remember it has a unit of seconds. And our max charge is going to be 30 e to the minus 6 times 12 volts, which is 0.00036 coulombs. We'll just have, and our next part of the method is to solve, so we're just going to go ahead and put these two sections together. And then we have QT equals Q max times 1 minus e to the minus t divided by tau. Well, we want to find out the QT is 0.99% of Q max. Or excuse me, 0.99 because it's 99%. So what we want to say is 0.99, or you could say, if you don't know, if it's not as simple that way, you could say 99 divided by 100, which you will see when you put in the calculator, gives you just 0.99. So we will say 0.99 times Q max, which is, oh, forgot a 0, equals, now remember this is Q max, equals Q max times 1 minus e to the negative t divided by tau. Well, our Q max is canceled because they're on both sides. So we have 0.99 equals 1 minus e to the negative t over tau. Whoops. Okay. So then we're going to bring this guy over to the other side and make him positive. So we're going to have e to the minus t over tau equals, we still have a 1, and then we're going to bring 0.99 over to this side, and we will say minus 0.99 equals, and then what we'll do is, because we need to find what we're looking for here is t. We're looking for tau, or excuse me, we're looking for t, time. And so what we need to do is we need to take the ln of both sides. So that way we can get this guy down on the ground so we can do something with him. But when you take the ln of one side, you have to take the ln of the other. Okay, so ln of e equals 1. So that's just going to come down like this. We don't have that trick over here, so we're just going to have ln of 1 minus 0.99. Then we need to multiply both sides times negative tau. That'll get rid of that. And our negative. So now we have t equals negative tau, which we know up here we found was 0.6 seconds. So it's going to be negative 0.6 seconds times the ln of 1 minus 0.99. All right, let's put this in our calculators. And we get that the time that it takes for our capacitor to reach 99% of its full charge is 2.76 seconds. Well, what if you wanted to know, because we talked about the discharging of a capacitor, what if you wanted to know the time and the charge and voltage and current that has to do with discharging a capacitor? Well, remember we said if we discharge a capacitor, okay, so we have this problem right here. And it says that the RC circuit has R equals 4.2 kiloohms and a capacitance of 4 times 10 to the minus 6. That's what micro stands for, microfarads. The capacitor has a voltage V0 at t equals 0 when the switch is closed. How long does it take the capacitor to discharge to 0.4% of its initial voltage? Okay. So for this one, let's go ahead and let's write down what we're given. So we're given that R equals 4.2 times 10 to the 3 ohms. We're given that the capacitance is 4 microfarads. And we know that the capacitor is at V0 at t equals 0 when the switch is closed. How long does it take the capacitor to discharge to 0.4 over 100, because that would be 4.4% of V0. Okay, so what do we need to know? We want to know the time. And the equation that we'll use here for discharging capacitors is, and the C is for capacitor, equals V initial E minus T divided by tau, which in this case, remember, tau equals RC. And for the the voltage that we're looking for, right, it's going to be this, the 0.4 over 100 of V initial. So VCT, so it's going to be 0.4 over 100 of V initial. So let's put, well, you can put it in your calculator, but when you're dividing by 100, you're just going to move back 2. So then we will have 0.004 of V initial is what the V at a certain time will be. So we're going to plug this in for this. And so we're going to have 0.004, this will be our substitute part, 0.004 V initial equals V initial times E minus T divided by tau. All right, so then we can divide V initial away. That's gone. Now we have 0.004 equals E minus T, and I'm going to go ahead and take this tau and sub it in now for RC so we see that clearly. So we will have, we're going to need to take the ln of both sides to get this exponent down so where we can do something with it. So that goes away, it's just 1. Then we have negative t divided by RC equals the ln of 0.004. Multiply both sides times RC. And then we have negative RC to get rid of that negative. Can't have negative time. All right, so then we have negative, our R is 4.2 times 10 to the 3 ohms times C. I'm going to have to move this over some. Times C, which we have as 4.0 times 10 to the minus 6 farads, times the ln of 0.004 equals T. And then we'll put that in our calculators. And we get that the time for the capacitor to discharge to 0.4% of its initial voltage is 0.0927 seconds, which is approximately 9.3 times 10 to the minus 2 seconds. And those are some of the ways that you can use these equations. So what I do is, my professor allows us to have an equation sheet for our exams. So I would have a section that would have things like this for discharging capacitors, and for the ones that we had up top for, for charging capacitors. In fact, what I'm going to do is I'm going to gather those really quickly and put those on the screen so you can also put those on an equation sheet if you like and have them all together. Okay, and here they are. So we have, for the charging capacitors, we have all of this right here. And then I wrote a little side note. These are ones that are already, if you're not comfortable manipulating the equations, you can just write these out like this. How long for the current to drop from some I initial to some other I final. Those are helpful. This is the same equation except for V. We have subbed in IR. Remember, we can do that because V equals IR. And your discharging capacitor equations would be right here. And for these, this is what we just did, how long it takes the capacitor to discharge to a percent of its initial voltage. This is what we did. We did the percent of the V initial, and then we divide away the V initial. And then you'll see here, this is the solving for the time. All right, I hope this was helpful. Keep practicing.